Hi, I'm guessing I was just introduced, but I'll say it again. I'm Zach Weiner. I've been getting my PhD in physics at the University of Urbana-Champaign. As of recording, I actually just defended my PhD a week ago, and we'll be moving on to a postdoc at University of Washington in Seattle, which I'm really excited about. And I'm also excited to tell you about some of the work of my thesis, which was trying to use gravitational waves to learn about the reheating of the universe after inflation. So time is really tight. So I thought I'd start by teaching everyone general relativity, no problem. So this is Einstein's equation written in its most opaque possible form. So Einstein tells us that space-time itself is dynamical, and in fact that the dynamics of space-time are governed by the matter content within the universe. And furthermore, space-time itself determines how matter evolves. Now, two of the earliest predictions made by general relativity were that the universe expands and that particular configurations of stress energy sources gravitational waves. And these are the two phenomena that I'll be talking about today. Now, if you've ever seen a talk about cosmology, you've seen this horribly cliched image, which I essentially just put up to give you a picture for the expansion of the universe. So, the universe is big today, it was smaller yesterday, and, long enough in the past, it was so much smaller that it was filled with a hot, dense plasma of all the particles of the standard model, which were in thermal equilibrium. And after enough time, that plasma ceases to be opaque to the photons, and the photons are then able to free stream from the so-called last scattering surface to us throughout the history of the universe to today. And we observe these photons as a relic background of microwave radiation that's called the cosmic microwave background. And we measure this background, and here it is. You might look at this and say, wow, that's really inhomogeneous. There's a lot of features in there, but what you have to realize is that this is the sky map of the temperature fluctuations in the cosmic microwave background after having subtracted off a mean component, which is 10,000 times larger than the fluctuations you're seeing here. And this immediately poses, one of the biggest problems in, the old theory of the Big Bang, which is that the universe isn't old enough for it to completely agree on the temperature of the photons across such disparate length scales. And it turns out that our leading solution to this problem is to invoke an earlier phase of accelerated expansion, which gives a causal mechanism for disparate parts of the universe to know to be at the same temperature. Inflation also happens to explain why the universe is so geometrically flat, why there are no monopoles and all these sorts of things. But our most sort of exquisite evidence for inflation is just how precisely it predicts the specific angular power spectra that we measure from the cosmic microwave background that we observe. Now, inflation itself is not free of theoretical issues. One of the foremost is that, as I mentioned earlier, we know that the early universe was extremely hot and extremely dense, but our microphysical models of inflation generically predict that inflation ends and the universe is in a cold and empty state, just completely devoid of particles. So the problem of reheating is to answer, where did all these particles come from? How did the standard model first get produced? So our leading models of inflation involve a homogeneous inflaton field, which drives the accelerated expansion and eventually starts to oscillate. So the entire universe is just this inflaton field that's oscillating in time. And it turns out that this oscillation can drive resonant instabilities in any other fields, any other particle species that are coupled to the inflaton. And this phase where resonant instabilities are exponentially enhancing other fields is what we call preheating. Now, to sort of get a picture for for how these resonant instabilities work. Imagine we have some field fluctuation that's a ball in a little bowl. And this purple bowl is going to deform with time, and that's exactly analogous to the sort of effective potential that's coming from the time dependence of the homogeneous oscillating inflaton field. And so if the characteristic oscillation of a particular Fourier mode is not timed correctly relative to the oscillation of the background with time, then the mode is just going to kind of sit there. It's not going to grow in amplitude. But for other specific wave numbers, the timing can be such that the amplitude of, in this case, the ball's oscillations grows exponentially. And so you can see that the potential is flattening out at precisely the right time for the ball to gain significant amplitude. And this parametric amplification is pretty much exactly analogous to what happens for fields coupled to the inflaton. Now our picture for this in real space is like this. So these are 3 panels of the density contrast in the universe. Starting off with some small initial fluctuations on the left, and that's just coming from the quantum mechanical vacuum. And then during this parametric resonance phase, the long wavelength modes are exponentially amplified, and that it can be understood in a linear analysis. And so you can see where the darker spots in the initial conditions are the spots that are the dark red after the phase of linear amplification. But these fluctuations become so large that nonlinear interactions become really important and propagate power to smaller scales. And so this immediately tells you that we're going to need computers to actually solve this problem correctly. Fortunately, the fact that the mode amplitudes grow so large, that these fluctuations get so big, means that quantum effects are unimportant. And so what that leaves us with is a classical field theory problem. Mathematically, what that just is a initial value problem of partial differential equations, which we can get away with the most simple discretization onto a 3-dimensional grid and evolve in time. And here are for the model that I'm going to be specifying to the equation, the full nonlinear equations and their horrific glory, and we solve those, evolve those in time along with the expansion of the universe and as I mentioned earlier, gravitational waves. Now the software that I developed throughout my PhD is a Python package I called PyStella. Don't ask about the name. There's not really good reason for it. It's parallelized with MPI, and it's accelerated with PyOpenCL, so it can run on GPUs or CPUs or pretty much whatever you want. And I decided to make use of a really nice, a fantastic runtime code generation framework called Loopy. And so, I was honored to have the chance to contribute to a special issue of Computing and Science and Engineering magazines, July, August special issues this July, on scientific computing and high performance computing with Python, where I sort of described the philosophy of PyStella as far as addressing the performance portability problem. And so if you're someone who dreads having to rewrite your software every single time a vendor decides to introduce their own programming paradigm, then I encourage you to take a look at this, what's going to be a really interesting issue, to see how interpreted languages like Python may actually be a better solution to the problem of high performance programming. Okay, so I promised you gravitational waves, so let's get some gravitational waves. As you'll see in this movie here, this phase of preheating generates inhomogeneities extremely rapidly, and this rapid development of fluctuations of large amplitude generates the right kind of anisotropic stress that sources gravitational waves. And essentially gravitational waves just obey a linear, inhomogeneous, hyperbolic partial differential equation that's sourced by this anisotropic stress. It's no problem to solve that in tandem with the rest of the fields, including the inflaton that we talked about earlier, and to make prediction of what we would see today. Now, you all are probably familiar with the landmark first direct detection of gravitational waves just 5 years ago, and that was the signal from a pair of merging black holes, which induced these ripples, these gravitational waves in space-time that propagate to us today. That's a signal from a single event, and the kind of signals that are relevant to cosmologists are a bit different. They take the form of stochastic backgrounds of gravitational waves that sort of permeate the universe. They were emitted by processes that were active when the universe was extremely young, and have persisted, just freely propagating to us today, and well, hoping that they exist. And we would observe them as this stochastic background. Now, what I'm plotting here is for a bunch of both currents and planned experiments, the sensitivity curve as a function of frequencies for this variety of experiments. So basically, the lower the curve goes in the plot, the more sensitive this experiment is to gravitational waves, particular frequencies. And the important thing to bear in mind is that higher frequency gravitational waves correspond to smaller length scales. And those smaller length scales were the ones that would have been dynamically active and had gravitational waves sourced at earlier and earlier times. So this array of experiments, each being sensitive to a different range of frequencies, basically provides us possible insight into the early universe, when it was, even less than a second old, at a variety of times. Okay, so what is the sort of the prediction from our simulations from the dynamics of preheating that we would see today? Well, so here are the results from the two models that I've focused on the most during my my time as a graduate student. And so, ignoring this high frequency part of the spectrum, that's just, an artifact of the quantum vacuum, that the physical signal takes the form of, essentially a sort of bumpy thing that peaks at frequencies as high as a gigahertz. Now, if you paid attention to the horizontal scale on the previous slide, you'll see that, all of the experiments that we were really talking about, whether currently taking data or planned or proposed, none of them come remotely close to gigahertz. And so that's pretty sad for our prospects to directly detect these signals and be able to place constraints in these models. But the other thing to notice is that these signals are rather booming. They peak at 10 to the minus 7, and 10 to the minus 7 on this plot would be within the sensitivity of all of these experiments. So it's kind of unlucky that gravitational waves become so much harder to directly observe at higher frequencies, but we do have hope in the form of an indirect constraint. Now, gravitational waves themselves actually also affect the expansion of the universe. They look like something that's radiation, and so they contribute to the energy density in radiation. And current experiments actually measure the budget of the energy budget in radiation to precision of a few percent. The next generation is going to improve this significantly, and so just from disallowing radiation beyond what we're currently allowed in the present universe, we can actually place constraints in these models. So on this constraint plot and the sensitivity plot, this indirect constraint takes the form of this gray band, and so that's the current constraint, and the next generation will maybe move down that far. And the important thing to realize is that gravitational waves which are subject to this constraint are those of arbitrarily high frequency. In particular, those gigahertz signals that I showed a few slides ago are going to be subject to this indirect constraint because, all of these frequencies gravitate like radiation. And so, this slide gets a little bit technical, but I just, put it up here as evidence for what I'm about to tell you, which is that we actually can already constrain certain coupling strengths between the inflaton field that drove inflation and these coupled fields in this particular model that I'm considering. And curiously enough, this constraint turns out to be the strongest constraint on this model. Even stronger than sort of other observational signatures that you might get out of it. And the next generation may even be able to rule out the entire regime in which this model efficiently preheated the universe, efficiently depleted the inflaton of the energy density at the end of inflation. So it's rather amazing that this physics at such an early time, such a tiny fraction of a second, on the smallest of length scales, provides the strongest constraints in these models, and that was a really exciting result for us. And so at this point, I will switch to present me for questions.